This is our first video on angular momentum and its conservation. Before we start, let's just review briefly the many connections that exist between translational mechanics and angular mechanics. For example, translational kinetic energy, we know, has this equation, 1/2 mv squared. Rotational kinetic energy, 1/2 I omega squared. We took the angular analog of mass, which is moment of inertia, the angular analog of v, which is omega, and we get that same looking equation. Earlier, we did something similar with Newton's second law. Newton's second law in translation looks like that. What is the angular analog of force? It's torque. What's the angular analog of mass? Moment of inertia. What's the angular analog of acceleration? It's angular acceleration. So you can see that there are some relationships here between translational and angular. That trend is going to hold for momentum as well. Linear momentum is mass times velocity. Angular momentum, which we symbolize with a capital L, is the angular analog of mass, which is the moment of inertia, and the angular analog of velocity, which is angular velocity. Unlike energy, however, these cannot be added to each other, and let's try and prove that to you. So the units on the right side of this one will be kilogram meters per second. How about on this side? The unit for moment of inertia is kilogram meters squared. I don't know if you remember that. And then the unit for omega is radians per second. Now, a radian is kind of a nothing unit, so that sort of doesn't really count. But look at that. Those two are not the same unit. Kilogram meters per second and kilogram meters squared per second are not the same. So we cannot add linear plus angular momentum like we can do with kinetic energy. Part B, the net force on an object or system is the time derivative of the object's or system's momentum. Part 1, write the calculus type equation for this statement. The net force is the time derivative of momentum. We've seen that one before. Therefore, if the net force on a system equals 0, then its momentum later must compare how to its momentum now? They have to be the same. According to that equation, if the net force is equal to 0, that means that the momentum is not changing. So its momentum now and later must be the same. In other words, momentum is conserved if the net force is 0. I just recopied this statement here at the top from the previous page. The rotational analog of Part B's opening statement is what? Well, here is Part B's opening statement. The net force. What's the rotational analog of that? Well, that would be the net torque on an object or system is the time derivative of the objects or systems. Well, when we're talking linear motion, it's force and momentum. When we're talking rotational, it's torque and angular momentum. What would the calculus equation look like for this? The net torque is equal to the time derivative of the angular momentum. In words, write a rotational analog to the Part B2 question and answer. Well, that's going to look like this. We could look back on the previous page if we wanted to. It talks about the net force on a system and its momentum now compared to its momentum later. And this statement here is, if the net torque on a system is 0, then its angular momentum later must be the same as its angular momentum now. That's what this equation on the right side of the screen says. If the net torque is 0, that means that the angular momentum is not changing, And if the angular momentum is not changing, another word is conserved. Angular momentum is conserved whenever the net torque is 0. Let's give you a couple of other quick equations for angular momentum. We're not going to explain all these quite yet. R cross P is one way to do that. Another way to write that would be R cross, well, what's P? P is linear momentum, m times v. Those are possibilities. The magnitude of angular momentum, you remember when we do a cross product, we multiply by the sign. The cross product, you use the sine function. And for the dot product, you use the cosine function. And here's how I remember this. Cross product, the dot product is also called the scalar product. Look at this. That one starts with a C, and the trig function starts with an S. This one starts with an S, and that one starts with a C. So the trig function that you use is not the one that is in the term for the product that you're doing. Cross product, use sine. Scalar product or dot product, use cosine. That's just a little mnemonic that helps me remember when to use sine and when to use cosine. We could also then say R, M, V, sine theta to find the magnitude.